Okay, good evening, everyone. If you could take your seats, we're going to be starting in a minute. I'll give everybody a chance to find a seat. All right. Good evening, everyone, and welcome to the AIAA Dryden Lecture in Research. My name is Fay Collier, and I serve on the Honors and Awards Committee. The Dryden Lectureship is one of the most prestigious lectureships bestowed by the Institute. The award emphasizes the importance of basic research in advancing aeronautics and astronautics. Since the inaugural lecture in 1961, it's been a catalyst for sharing research advancements and knowledge. This premier lecture is named in honor of Dr. Hugh Dryden, a renowned aerospace leader. He was the director of the National Advisory Committee for Aeronautics, or NACA, as many of us know it by, as well as the first deputy administrator of NASA when the agency was created in 1958. It is now my distinct honor to introduce you to the winner of the 2024 AIAA Dryden Lecture in Research, Peyman Givi, who will deliver his lecture, The Promise of Quantum Computing for Aerospace Science and Engineering. Please allow me to share a bit of his biography describing his incredible career. Peyman is the Distinguished Professor and James T. McLeod Chair of Engineering and Professor of Mechanical Engineering and Petroleum Engineering at the University of Pittsburgh. Previously, he was the University at Buffalo Distinguished Professor of Aerospace Engineering from 1988 to 2002, where he received the Tau Beta Pi Professor of the Year Award in 2002. Dr. Givi has also worked as a research scientist at the Flow Industries in Seattle, Washington. He's had frequent visiting appointments at NASA Langley and Glenn Research Centers. In 2005, he received the NASA Public Service Medal. Dr. Givi is among the first 15 engineering faculty nationwide who received the White House Faculty Fellowship from President George H.W. Bush. He also received the Office of Naval Research Young Investigator Award and the National Science Foundation Presidential Young Investigator Award. Dr. Givi is a fellow of the AIAA, as well as AAS, AAM, APS, ASME, the Combustion Institute, and he was named ASME Engineer of the Year in 2007. He is currently on the editorial boards of the AIAA Journal, Combustion Theory and Modeling, Computers and Fluids, and Journal of Applied Fluid Mechanics. He received his PhD from Carnegie Mellon in 1984 with the Distinguished Alumni Achievement Award in 2022. He was summa cum laude at Youngstown State in 1980, where he was named the Distinguished Alumnus in 2004. His lecture today will address the second quantum revolution. We are now at a stage where we can use quantum science to invent quantum technologies. So now, please join me in welcoming our distinguished lecturer to present the 2024 Dryden Lecture in Research, The Promise of Quantum Computing for Aerospace Science and Engineering.
All right. Thank you very much, Faye, for the very magnificent introduction. And it's really an honor to be at this stage and receiving this award and actually be in the same sentence with Dr. Dryden. It's an honor. And I'm really grateful to the members of the honors committee at AIAA for selecting me. And I also, this kind of awards, you don't get them, for one thing or so. Many other people have contributed to this, and I'm really very pleased to acknowledge all of my mentors and advisors. There is a whole bunch of them, but at least some of the ones that I took courses with them and always go with them are indicated on this, and also my colleague at University of Pittsburgh, where I work now, and University at Buffalo. That's where I was before, and also Flow Research Company, and also my alma mater is at Carnegie Mellon and Youngstown State. Well, along with those, the other people have contributed a lot to what we do. Are my former PhDs. I've had the pleasure of working with a large number of undergrads and grads. I could only list the PhDs. And what's happening with a lot of them, they used to go to academia. A lot of people in the academia or government laboratories. But now, as you know, aerospace engineering is a very hard field. You do calculations on it. Everybody likes you. So now all the later ones are going to these data companies and software companies with salaries 3 times as much as of a full professors. So that's one good thing to be doing aerospace, but it is so hard. The students who graduate, then they can go to everywhere else. And I try to ask them to please, stay in industry, in aerospace, and be a professor. But they, when they see all the money, that's where they go. Now, one thing I do like to acknowledge, everything we have done that pertains to this particular research I'm talking about is primarily, is due to IFOSR. I feel very privileged to be in the program of Dr. Fariba Faroo in computational mathematics, who's supporting this work. And also our previous work on the subject was funded by Doug Smith and David Stargell. And, and I really should give a lot of the credit to Doug and David, because somewhere around 12 years ago at this meeting in the exhibit hall, they had this poster about quantum computing. And I know a lot of us, we were walking there at that time, we didn't even know what this thing was. And this was one of the view graphs that at that time, Doug and David, they had presented that they were envisioning this idea of moving towards quantum subject. And then to see that, if this could be used for the actual kind of calculation that aerospace engineers and scientists could use. And that, made us to think about this. And I have to admit, that was the first time I even thought about this whole subject. So, back then, if you wanted to study quantum computing, there was only one textbook. Seriously, there was only one textbook, and it was very good. It's a classic, but for engineers, it was unreadable. It was mostly for physicists to have a good knowledge of quantum mechanics. But throughout the years, many things have developed, and the reason that people have been start talking about it is because of the way that this Moore's law is coming to a point that people are thinking that the days of this law is finished. Just the rapid growth of the linear growth of the computer technology with years, and we are deviating from it. And this is the actual curve. And if you, for those of you who are doing fluid dynamic calculations, you see a direct correlation between the Moore's law and the way this large-scale DNS direct simulations of fluid mechanics is happening. So where do you go with this? Where do you go with that? Because as the transistors getting smaller and smaller and getting to the size of, where the quantum effect become important, what are you going to do with this? And that's where this whole idea of quantum computing has come to the interest of a lot of people like us. Now, if you look at what has been done, there is a lot of, if you're following the literature, you see that there is a lot happening in the literature about quantum computations. There is, every issue of Nature or Science, they're having articles on it. They have at least a journal dedicated to this topic. There is a whole variety of fantastic books being published, almost, 1 or 2 a year. And there is, now they have quantum computing for everyone, for babies, for smart people, and for people like myself. They have, this sort of literature, and it has come to get the attention of everyone in this business, even at very high levels. Now, that's it, the science of it. Then it has also gone to some of the fiction or some of the myth about this whole system. There is a whole bunch of things about, some of the mysteries of quantum computing. And if you have seen the new book by Professor Karko that is talking about quantum supremacy, that with quantum computing, all the problems of the universe could be solved, or by Professor Seth Lloyd, who basically says that the whole universe is a kind of quantum computations. And then there are others that they think that the whole thing is a hype. And since the beginning, as I'm working on this subject, this issue of a hype has been of a concern of people. How much of it is a hype, and how much of it is a reality? Well, I had the advantage of getting into this without knowing much about it. So I had to go learn everything by myself, and then look at it from the point of view of somebody who's in CFD, combustion turbulence, to see how can this thing be working or not. So I didn't have a prejudice about this. And that's throughout the years, this is what my experience is by learning what I have learned. So what is this whole concept of quantum computing? As you see any of the literature, it goes back to some of the early work of Richard Feynman, who actually suggested that if something is quantum, why do we solve it classically? That was the original idea. But if you really look at all the literature on this subject, you would see that there are others, that some of the names that I've listed there, and they have been looking at is a quantum phenomena can be described by a quantum computer and with a quantum algorithm. And so those are the two things that are different, which for us, is also very important, because they were interested at that point that if it, as a phenomenon is quantum, then you have a quantum algorithm and then a quantum computer to solve that algorithm. So, and these are all because of the advantage of this quantum formulation, as I will show you in a second. So what happened with the QC went to the subject of QC and quantum information. And as you all know, the Shor's algorithm in the mid-90s, that factoring of numbers, and then with the Grover search algorithm that made this whole business of quantum computations, quantum information a reality. That it is not just something in your mind; it can actually be used. And that was in the mid-90s. This whole birth of field of quantum computing and quantum information. So what is it? I mean, what is it, and how do we take advantage of it? And in order to understand the power of it, it's just good to look at the difference between actual quantum computing and classical computations. But in classical computations, as we all know, this is a concept of a bit. You have an on or off. That's what it is, 0, 0, and 1. And this concept of the qubit is, what is it? It kind of 0 or 1 or both. It kind of reminds me of myself as a foreign student when I came to US. Didn't know the English very well. People ask me, would you like tea or coffee? I say yes. They say, yeah. I mean, this is exactly what it is. Yes, I mean, it is 0 and 1. It is just the way that they describe in that, the figure on the right, you have, 0, the arrow going up, and 1 going down. And you don't have to be 0 or 1. You can be anywhere at this point. Of course, once you measure it, you are going to get either 0 or 1 in that frame, because that's what your measurement system is. So the reason quantum computing works so well, and it has potential for 2 reasons. One of them is just what I said, the concept of superposition. Superposition means that a quantum state, and this psi is anything that can be described in quantum, and that's the way the quantum physicists describe a vector, anything in a vector space. So it is a combination of zeros and 1, and which this is squared of this, and this is 1. So A0 squared is the probability being at state 0 and being at 1. So that was any state, any kind of system could be given at any of those positions. And it's a superposition of those positions. So that's what it goes. How can it be 0 and 1 at the same time? Just like this, Schrödinger cat being dead or alive at the same time. So that's what this whole concept of superposition is. Now, the second one that is very mysterious, and it's just really hard to explain after even working with it, is the concept of entanglement. Entanglement, the quantum is being 0 and 1, 0 being here, 1 being 1. It could be anywhere on this. And this is, with 1 qubit, the 1 qubit, and 2 complex numbers, A0 and A1, would be describing the state of the system. That's what it does. Now, what would be happening if you increase this number of qubits? If you go, for example, with 2 qubits, then these 2 things are going to interact with each other. And then if you have n qubits, you have 2 to the power of n complex number to describe your system. And that's amazing, because the power increases exponentially. And with just n equal 1,000 qubit, you would have somewhere around 10 to the power of 300 coefficient that can describe this. I never realized that number is that large until my physics colleagues told me that's more than the number of particles in the universe. And I asked them, are you serious? They said, yes. They said, if you don't believe me, go count them. Yeah, just. So having that much power, and the way that people who do this kind of business, especially in the field of many-body physics, that have to worry about the large number of particles, this thing has become a very, very powerful tool to be actually used for that purpose. And this amount of space that you can use for your computations has made some of the authors to even relate it to some of the things that's supernatural or whatever. So this is the background about it. And how do we use it? How can we, as aerospace engineers, how do we use it? Well, this is the terminology me and my colleagues used about some years ago. Now it has this terminology becoming very popular in the physics community, because now the physicists see that we are doing fluid mechanical combustion problems. Now a lot of physicists are getting into this business of coming from the field of many-body physics, and from that area to doing actually fluid dynamics. So the way I have divided this thing, and the way that this thing can be used for now, for us, is there are 2 ways that this quantum could be used. One of them that we call quantum ready. Quantum ready are the algorithms that are out there right now that have been developed by all quantum physicists and mathematicians. But this algorithm could be used right now for the purpose of our calculations. This is what quantum ready is. And the other one that we called it quantum inspired, and this is becoming one of the hot words in the physics community. These are classical algorithms that their origin is from quantum physics. And as I will show you that some of these algorithms have become very powerful for actually solving the problems that we are interested in it. I wouldn't have the time to go through all the mathematics of it. There is several papers on the subject, that you can look at to see some of the basic mathematics of it, but I will just follow through what needs not to be described. Well, the first thing is, if you want to have a quantum computer, universal quantum computer that are based on unitary gates. So as what we have classical computers that they do with this logical gate, on a quantum computers, we have all of this gate that performs the calculation in a unitary manner. Being unitary is good because it would allow you to use some of the quantum algorithms, but it could be bad because some of the problems that classically we have when we construct is Hamiltonian, those Hamiltonians cannot be described by unitary operations, and we have to do some tricks to it. So those are where these things are, where these quantum computers are. Now, what are the quantum-ready algorithms? This is something that for us, we had to search to see what are the algorithms that are out there. And these are some of the way that actually these algorithms right now could be used for the kind of problems that we are doing. So basically, the most important one, if you have a systems of linear equations, now it has been very recently proven that quantum algorithm exists that has a quantum advantage over classical simulations. The Monte Carlo sampling is another one, and that's something that we use all the time. If you have solution of a sparse linear algebraic equations, that one is also, those are the ones that right now this quantum algorithm could be very useful. We have to happen to show that in the case of, for example, large eddy simulations, which I've been spending a lot of my time doing, earliest by Monte Carlo methods. And a lot of the students, they don't like this many number of years to do one set of calculations. So there is always looking for a ways of to improve the calculations. And these quantum algorithms that are out there have shown to provide advantage for that. So, for example, this is from showing the speed up of a quantum algorithm in comparison to the classical one. Of course, right now, this is an algorithm that exists, but in order to run it right now, you need the large number of qubits that is not available for us to run at the moment. But the algorithms are, the quantum computer is not. One of the examples. Now, there are some other examples too to extend in this for reacting flows or whatever, but there are problems with quantum computations. With quantum computers. And these are the problems that are right now what makes people not to be able to be using them at the point, or for places for Google and IBM, not to be constructing them. And a major problem is, this whole concept of entanglement of the qubits when they interact with each other, but they also want to interact with outside. Anything outside, they want to interact with it. And to keep it isolated is very, very difficult, to keep the isolation of them. And then the fidelity of the gates, all these quantum gates, they all introduce errors. And when you can imagine when you are dealing with some computations that your actual gate are basically working on atoms, a lot of things could go wrong. You can use the coherence. And in some cases, depending on what kind of a qubit they have, this whole organization of the where is the qubits and how they are located, where they are, and all that is also an important thing to worry about. Yeah, this particular one is from one of the most recent IBM systems with 127 qubit, and they have to put them in a system that the interaction between them is to get to full advantage of entanglement. So this lack of coherence or decoherence, slightest happen, you lose whatever it is, and this is the number one issue that, all of these quantum people are trying to solve right now. So until they solve it, what is the alternatives? What can we do right now as we are doing it? So as we are using those algorithms, but we can also, what else are there that we could use? Well, the first one is these machines, the NISQ computers, in which, there are errors with it, but these are the kind of errors that maybe you can tolerate, or at least for some of the operations, you can tolerate this error for at least some duration of times. And a lot of these NISQ computers, which is actually very useful for us in the form of actually getting experience with these quantum computations. IBM Qiskit, for example, is one of those that you can play with those simulators, and in order to run your algorithm to see what you get. So those are the NISQ machines. The second one is what a lot of people in chemical kinetics are interested in, is hybrid calculations. In fact, you do some part of it on classical and some part on quantum. But when as you read something from quantum, you destroy whatever information you had, but you feed it back to a classical. And you can do that kind of a repeat in a form. And the third one is called the analog simulators and mirrors, that these are for a specific task in which they do not use the digital gate-based computations, but they use them in an analog sense. And these are, they derive the Hamiltonian system in an analog fashion that is just a lot more error-free. But they are very limited, and it can be used for a specific class of problems. They're not as versatile as what a dream is about the universal digital computations. So these are what it is in the market now, as you might, this one, I think I finalized it last week. Maybe by today it will be changed. So the number of qubits is increasing or whatever, or people saying that the number of qubits that this company said is not correct. So this is just what at least what it is out there. But one of the things interesting is that there are a huge number of startup companies. And last year we had a position open in quantum computing at Pitt, and we had a lot of international people from other countries applying for the position. They had no interest in the job. They just want to come to US to have their startup companies. We found that many people have ideas in this business. There are a lot of startups. Now, the second one, which I am really excited about, and I think you will be, is a quantum-inspired algorithm. And these are the ideas that, again, come from the concept of many-body physics, that people say that we are dealing with Schrödinger equations, very complex equations, and with the Schrödinger, we want to use them for a system, and there are ways of dealing with them called the tensor networks. The tensor networks. And that's a name, I bet you in 5 years, everybody in the aerospace community is going to be using it, tensor networks. And it has nothing to do with the TensorFlow of Google, tensor networks. What it is, we said that we are dealing with complex phenomena, turbulence, combustion. These are, a lot of interaction. Why can't we use this whole idea? And this idea, the quantum-inspired, is, tensor networking, is based on isolating a very complex equation to an ensemble of tensors. So, for example, the original idea coming in with, using the Schrödinger equations, and these are your vector space that is, n-dimensional tensor. In theory, the computational time of it goes exponentially, the computation of it. But in many cases, it's possible that these computations could be polynomial now. And, if you could find those and restrict your space of computation to that space, then you can do those computations. And, I have been doing CFD for now 40 years. So always trying to minimize the computation is an important subject. So what this tensor network does is that, well, we have from many body physics, a large number of atoms, we try to compress them to consider, the few body physics. So we said that, okay, how about us? We are doing the DNS, we are doing direct numerical simulations, large number of grids. Is there a way we can do them in a compressed format? Well, as somebody who has been doing LES myself for I don't know, for 25 years now, we always worry about the scale. Let me filter it and resolve the scale. Well, maybe there is other ways of looking at it. Don't look at the scale, look at something else. So what this one is, the whole idea coming something is called the Schmidt decomposition in quantum theory. And what it says, if I have a quantum state, as n with an n-dimensional tensor, the Hilbert space of it, if I divide it up at the tensor product of two Hilbert spaces, just two for this one, I can write this thing exactly like this, with this gamma is the number of this singular value decompositions. It is pretty much a lot like when you do SVDs, when you have those, and this gamma is usually large. But if there are cases in which if I make this gamma to be chi, a lot smaller, then I would live in a much smaller Hilbert space of these computations. And that was the whole idea, the simple idea, but does it work or not? So what we have done, for example, in this case, if I have n-dimensional tensor of order n, and I do a system of SVDs and contractions, I could make them to be as a tensor product of all of this lower order tensors, in which there is a bound between them. And this is the physical bound between them. And that is the bound, if I can decrease that size, I'm using the structure of my system in order to make it to move toward a smaller space for which I can do the computation. And that's the whole trick of it, and it works really nice in fluid mechanics and combustion. So how do we demonstrate it? How do we demonstrate it that this thing works? So I try to do it for the DNS. Those are the areas I know, fluid mechanics and combustion. And we do with LES and RANS. And, said, what method in LES and RANS we use? I use the best method there is, the PDF and FDFs, right? And LES, for those of you who do LES, FDF is by far the very best one. Yeah, because, not being prejudiced about it. So these are the methods that we have used to do for our LES and to demonstrate it. So this is for the case of a DNS, is a homogeneous turbulence, is a Taylor-Green vortex. It doesn't matter, it's a homogeneous turbulence, it's a high Reynolds number. So we compare it with a DNS in which we resolve the entire scales, the entire scale of the flow, very expensive simulations. And then we consider a case that it is under-resolved DNS, in which that we didn't resolve them. We didn't use any subgrid model, just under-resolved DNS. And we compare it with a quantum-inspired MPS called matrix product state, is one way of doing tensor networking. One of the ways, there are many ways of doing those. And we perform the calculations. And for the, going back. For the MPS, it has the same degree of computational complexity as under-resolved DNS. So if it be the same computational complexity as that, then it is useless, right? It has the same computational complexity as under-resolved DNS. But as you would look at all the flow structures, including the statistics of it, compare very well with the DNS data. There is a paper published in Nature Computational Science that gives all of those kinds of a comparison if you're interested. For the case of vortex dynamic in a shear flow, the same thing. Again, as you know, with the Kelvin-Helmholtz instabilities, they're very sensitive to the background of the fluctuation, how this thing is going to grow. So what we are showing in this one with the DNS, the quantum-inspired matrix product state, and the under-resolved DNS. And this one, probably many of us have already seen that. If you don't have under-resolved, you have things that are under-resolved, this, the growth instability mode would be very different from that with the accurate simulations. And this one with the quantum-inspired, the two schemes seem to be comparing very well. So the dynamic of vertical structures are very much the same. And important thing from engineering standpoint, if we look at the Reynolds stresses, Reynolds stress is a turbulence. People are very interested in it. You can get, the sign of, especially with the sign of Reynolds stresses, which one you would get. And with the DNS and quantum calculations, they're pretty much on top of each other, whereas the under-resolved DNS, as we already know, is failed to actually capture those kind of phenomena. Now, this is the most important figure that I think I can show. It's just going to show me the spectrum. And that shows the correlations between the different structures of the system. So there are 8 panels there. Those are, 8, the velocity vector at 8 different times. So what this thing is showing is that these are all the scales, that on the x-axis is all the scales that the DNS try to resolve. The DNS, we have that much scale that we're trying to resolve. But now, if you perform this kind of a tensor networking, as I talked about, 99% of the correlations are covered by this dashed line. So it means that whatever is happening under here, this is all that you need to perform your computations. The rest of the space that we are having for DNS is basically, it is there, but it is being actually not very useful for our purpose. So if we can concentrate. So in LES, what we do, we truncate the scales, and the scales of the flow with the length scale, and we model the subgrid, right? So with this one, we have, all of these areas that does not need to be captured. So if you can concentrate in that area, you can do, much better computations. The method has been very nice in capturing shocks and also for resolving for the flames. So these are the ones that we are interested in for doing compressible flow. If it actually capturing the shock, do we need more of the Hilbert space for a computation? And you really don't. I mean, you can still with a small part to capture the shock and to capture the physics of turbulence interaction with chemistry. Okay. So in the case of, that was all the calculation for the case of, for the DNS. Then we said, okay, let's go with the case of RANS and LES. And we said, okay, let's consider some Langevin equation in which we know an analytical solution, and also filter density function methodology for a complex case in which we have been resorting to Monte Carlo methods. Okay, so this is the first one, that doing the consideration of a very, very popular model called the model of turbulent scalar mixing, in which you would have, mixing of two fluid, the PDF of the fluid, Z is a magnitude of the scalar, and the PDF will start at time of the 0 with some double delta as it mixed, comes to a single delta, there's homogeneous turbulence involved in that thing. And these are the kind of calculations that typically, are being done typically by Monte Carlo methods. If we do this, and these are, the resolution in the Z space is about 128 to perform this, but the MPS is very powerful in capturing this with this interaction of only 4. With 4 out of 128, you can capture this exactly some of the moment. If you go to 3, then it doesn't, deviate from analytical result, from some of the mean and RMS values. Now, the one that is a lot more complex, doing the LES, in which you have a chemically reacting flow, A plus B going to product in a 3-dimensional simulations. And this very simple case, homogeneous turbulence, if you have only 2 scalar in a 3D turbulence, your PDF or FDF is a 5-dimensional thing. In this business, we could never do those high-dimensional calculations. We always done Monte Carlo. So, I mean, as you know, I do not know people doing that many, large number of dimensions calculations. So this is the calculation, again, BTF. And these are simulations we're doing that with 128 to the power of 5. So that's actual space that is needed. But again, we are not in that big space, with a much, much smaller space. But effectively, we're doing 128 to the power of 5 simulations and showing that the joint PDF of a fuel oxidizer starting from non-premix reaction and going to the zero, where both react and the PDF going to the zero, both concentration going to reactant being consumed. So the fact that now we can do this kind of calculations without going to doing Monte Carlo, that's actually very pleasing for a lot of us, for many of us who have been doing this kind of calculation for a very long time. And of course, if you increase this interaction with chi, the infidelity of the model would decrease. So in this case, 128 was the maximum. So this is the total amount of infidelity that even, for these values, 16 is pretty much, you can get, very, very good kind of an agreement with what the exact result should be. One major advantage of this kind of a calculation they do, because it came from the quantum world, but it is actually now, it is very nice to be using them for actually on the quantum computers. So this tensor network MPS, they're ideal for running them. And in fact, about a month ago or so, IBM came up with a new software that is used for the purpose of MPS. That if you have written something in the MPS, there are very nice quantum circuits that you can use to do your calculations. So it is conceptually a mathematical conception, but it is going there to the actual quantum simulation that you can use for actual computations. So where is the future of QC? Where we are with this, I borrowed this figure from what Professor Perskill at Caltech presented years ago. But pretty much the whole idea is the same. The concept is the same. It is just that the years might be here and there. So where we are, the number of physical qubits that we need to do the kind of calculations. I mean, what people were typically saying that we need an order of 1 million of them. About 1,000 logical qubits. Each one of them has 1,000 physical qubits. So it is order of 1 million. And this is where the error corrections threshold is. So this is where we are now. We are still at an area that our error that we get is more than that we can handle. So as years go by, the hope is, the number of qubits increase and the magnitude of the error that you get would decrease. And these are, if you look at the websites of IBM's or Google, they are all having plots of like this projecting how they are going to get them. And with all of those things, I want to quote that from Nobel laureate Bill Phillips, that what we have as tomorrow's quantum computers compared to today's supercomputers, like we're comparing this with the abacus. That was the idea is. I don't know when it is going to come true, but at least we are on the path to be getting there. So in summary, what I like to say about the quantum computing as far as aerospace science and engineering is concerned, we really do need to identify areas in which quantum algorithms could be useful. And as this power becoming more and more available, we should be really thinking about some of the game-changing applications. I was giving this talk at the press, talking about quantum computations for LES, and somebody said, well, if a computer is so powerful, why do you want it LES? Why don't you just do the DNS stuff? Which is true. Our way of thinking has to be changed. And we have a game-inspired, a lot of the quantum-inspired algorithm. I really think that those are the way to do. The people in physics area, they're heavily onto it, and I think people in engineering are getting into it as well. All of this stuff that we talked about, it has been summarized in this NASA report and also published as a survey article in AIAA journal you're interested in. I started this talk with acknowledging a lot of people, but also I want to acknowledge the people who are working with me now. These are a group of fantastic applied mathematicians and quantum physicists at the University of Pittsburgh, and a lot of my colleagues that I collaborated with them, and most of them are actually in Europe. Europeans are a lot more interested in this, and also people at Google. So it was really a pleasure to be working with them, and I'd like to acknowledge them. And I thank you very much for listening to me. Thank you.
Thank you very much, Peyman, for a very, very interesting discussion on quantum physics, quantum mechanics, quantum computing. It's my pleasure at this time to present the certificate and the medal for the Dryden Lecture and Research for 2024, emphasizing the great importance of basic and applied research to the advancement in aeronautics and astronautics. This is a salute to research scientists and engineers, and this is awarded to Peyman Givi, the promise of quantum computing for aerospace science and engineering. Thank you for that lecture.
Thank you very much. I appreciate it. Thank you.
And here's your medal.
Oh, beautiful.
And if you don't mind, I'm going to put it around your neck.
Okay, thank you.
Let's get this out of the way here.
Yeah, I was worrying about this. I have a big head. So.
Okay, and I think we're going to have a photo opportunity here. I want to make sure I get this right. Okay.
Thank you.
And I think we have probably about 13 minutes for questions from the audience. And I'm going to start that off, if you don't mind. Also, I encourage folks to use the tool for submitting questions while we start off with a softball question.
Okay.
So if I'm a young person at this point in time, what advice, and if I decided I wanted to get into quantum computing, what advice would you give a rising senior in high school or even in university? How would I get into this? And just
fantastic.
Help us out a little bit there.
Oh, absolutely, yeah. Well, actually, when I got into this, I'd taken a course in physics, modern physics undergrad, but touched upon quantum. So I had to start from zero. But now a lot of universities, they are having programs in there. We offer right now, because of the interest, we offer a course at the undergraduate level called Quantum Computing and Quantum Information. We even have on the undergraduate, we have a certificate for this, that people take some courses to be taken to become expert in that area. We have started a master's program in quantum computing, in which the students can actually directly apply and get a master's degree in quantum computations. Now, this thing with the whole quantum, we had a panel this morning about the boundaries of computations. It is not just associated with the quantum, but with anything else. The boundaries of science are changing. As aerospace, we cannot just, stay with aerospace to understand, take flight dynamics and, fluid mechanics. The boundaries are changing. The same thing as artificial intelligence came in, a lot of the machine learning and data science is coming in. We had to go across the discipline to take courses on how to manage the big data, the analysis of, how to manage them, the data learning, the statistical learning. People have to go back and, start taking courses in those areas. The same thing would go with quantum computations. If you want to learn this, and this is going to be happening, which is actually a lot faster than people expected. So the new generation of a student, they have to be starting taking quantum courses, taking, basic quantum information, like they are doing it with machine learning. Now, in all the engineering, all the engineering students, they are all taking a course or two on fundamentals of machine learning, and that the same thing has to be done with the quantum. So at the undergraduate level, we encourage them to be taking at least a course in quantum and also a course in a statistical mechanic as much as they can. Try to carry them more on the physics courses and, rather than engineering applications. And then we have other courses that they can they can learn and move forward.
Okay, so I've used the tool here. We've got a few questions coming in. If you don't mind, I'll read a couple of those for you.
Sure.
We still have 10 minutes to go.
Yeah.
But I have one more question for you at the end. Okay, right now our top vote getter in terms of questions is as follows. You mentioned that there are many problems to solve in order to make QC actualized in engineering. What is the current technology readiness level, if you're familiar with that?
Technology for what?
Technology readiness level. You could also think of it in terms of a capability maturity matrix or level. I'm not sure how you think about that. What is the technology roadmap from where we are today? This is a secondary question. So what's the readiness level and the roadmap? You talked a little bit about that.
This is really a good question. You know, the people that we talk with, places like Flatiron Institute or Sandbox, these are the people that are not aerospace engineers, they're all physicists. They are ready to move into this. You know, they're hiring our students, our postdocs, that they want to do plasma calculations, they want to do turbulent calculations, they want to go to actual engine calculations. So if you look at from the people who are coming from that side, people who develop these codes, they are ready to be handling physical problems. But us as engineers, we are not ready yet. If I go to any of the aerospace companies or aerospace things, say, look, let's do this. It's going to take time because traditionally in aerospace we have been very, very conservative to be moving toward areas that is forefront of doing this kind of calculations. I think with these ideas of, this tensor networking still is a research. It's not at the point of the technology. But now with it, we have passed from CPU to GPUs. Now we are heavily into TPUs. And with those TPUs, they can do this calculation I showed you with the chi. These are very, very, very large values, that chi value. So those are actually ready. I mean, people think that, this kind of calculations of what people are doing with DNS are all within reach. So I would say as far as the roadmap of a turbulence is concerned, I really like to see within the next couple of years how these kind of calculations can actually, to pass the state-of-the-art DNS.
Okay, thank you. So we have another question here. Is there a way that we can begin identifying problems that are well suited to solving using quantum methods?
Well, yeah, I mean, depends on what problems you have. I mean, there are a lot of problems that if you're using any kind of optimization, any kind of optimization-related problems, a lot of this analog computation could be useful. In fact, I know that at NASA Ames, they have had some of those D-Wave machines that they have been dealing with some of the problems, optimizations, and machine learning. Some of the other problems that it is in a hybrid computations, I haven't done them, but people who do a lot of chemistry, chemical kinetics calculations, they have been using them for a lot of this hybrid kind of computations. None of the other things that, all of these quantum-ready methods, none of the quantum-ready methods have not been applied on a quantum machine yet, simply because all of these algorithms require, very, very large number of qubits. And right now, we don't have any of those machines with that large number that the quantum advantage could be demonstrated.
Okay, thank you. Mind if I take one more from this list?
Of course, yeah.
Oh, okay.
That's when you are.
All right. I think I should be marking these off, but I think the next one is, does a calculation on a quantum computer exist as a distribution that requires multiple executions to resolve?
Well, yeah, very good question. See, these are, whenever you're solving Schrödinger equations, it is still probabilistic. At the end, all of these algorithms, I mean, they're not Monte Carlo in the sense that we are thinking of. All of these algorithms, they do the repetitions of them, so because when you go there and you are in a quantum state and you read them and you read the result and you destroy the result. So all of them, they have an element of repetition. You know, how much of this repetition you have to do. And a good quantum algorithm are the ones that they derive you to the correct solution, quickly. So you can always guess them. So, I mean, that's the whole idea. It's like, if I'm going to be guessing them and iterating to get there, is not very innovative. But the whole beauty of the way that the circuits and the algorithms are built to drive you toward that solution, that you are getting the correct solution and getting to them correctly. But they're all based on that concept. That's the whole business of Schrödinger. Schrödinger equation is basically a probabilistic equation. You know, so that's probabilistic. So you might think of, you know, the Monte Carlo, but it's not Monte Carlo. It's like realization of the quantum states.
So one last question, if you don't mind. You know that we've dabbled in low NOx combustor designs for aerospace applications, airplane applications, engine applications for a long time. How do you see, as an expert in that area, how do you see the student arriving at university, studying traditional courses work and combining that with a tool such as quantum computing? How do you see that moving forward and enabling us to get to some of these designs that we're interested in for aerospace applications?
You know, this is, actually we were talking about that this morning too on the extended the boundaries of computing. Yeah, the students that we get, we don't, a lot of times that because we're in aerospace and engineering, all of our funding is to deal with fluid mechanics, turbulence, combustion.
Right.
The students are coming in, they want to deal with this problem, but we say, okay, this is the tool that you have to learn.
Right.
So they have to go take a whole bunch of courses in high performance computing, quantum computing, all of these other courses to be dealing with this. The same thing for students we had who were doing machine learning for combustion, fluid mechanic applications. They do that. In fact, we have published papers in which we use machine learning or deep learning for combustion, for fluid mechanic. But the students, when they graduate, and that's a problem we have, they're so good in the other thing that they tend to go into that area.
Yeah.
And seriously, one of the challenges that we have, and this morning I was suggesting that really our government agencies, they should find a way of funding the students in computer science and engineering, not having necessarily, have it physical applications. Because when we train them, I mean, I'm a professor of engineering. We train them in this business, but once we train them, as I told you, my last set of 5, 6 students, none of them went to this area, and I really like them to send them to academia, to places like NASA that my former students used to go. But now they don't do this. It's just they go into this area, the salaries are much, much higher, and this other domain, they cannot compete with them.
It's not the only area where we're having this challenge.
Right.
All right, so please join me in one last welcome. Thank you for a very exciting lecture.
Thank you.
And indulging us in the Q&A session.
Thanks a lot.
Thank you. Well done. So that concludes our lecture for the evening. Thank you very much for your time and attendance.